Ever wish you could like bend light to your will? Not with mirrors or lenses or anything like that, but with magnets.
Sounds a bit like a superpower, doesn't it?
It does. But believe it or not, that's kind of what we're diving into today.
Yeah, that's right. We're taking a look at a research paper all about this wild concept of magnetic dislocations.
All right, so magnetic dislocations. What are we talking about here?
Well, it really is kind of like twisting magnetic fields to trap light. It's pretty mind-blowing stuff.
Okay, so that's our mission for this deep dive, I guess.
Hmm.
Figure out how they're doing it, why it's such a big deal, and what we can even use it for.
Exactly.
Sounds good. Well, I'm ready to dive in. Where do we even start with something like this?
Let's start with the basics. I think everybody knows what a dislocation is like in the real world, right?
I mean, you have like a wrinkle in your shirt or a fold in a piece of
Yeah,
paper.
exactly. It's a place where the material's structure is kind of disrupted.
Okay, but we're not talking about wrinkles in fabric here. We're talking about wrinkles in magnetic fields.
Exactly. And normally you'd need to physically change a material to create a dislocation.
Yeah.
But these researchers, well, they figured out how to create them within a magnetic field itself.
Whoa, okay, so it's like they're not bending a physical object,
Mm.
they're bending the magnetic field lines.
Yeah. It's kind of like they're tying a knot in the magnetic field.
A magnetic knot. I like that.
Yeah, so they're doing all of this using a virtual model, like a 2D lattice.
I'm guessing we don't need to get into the actual equations here.
No. We don't need to get into all that. The important thing is that this method could be super flexible.
Yeah.
And we could reconfigure it on the fly. I mean, that opens up some crazy possibilities.
Yeah, like what?
Well, imagine being able to just manipulate light whenever you want, changing its path, its properties, just by tweaking a magnetic field.
That's pretty wild.
Yeah, it is.
Okay, so we've got this magnetic knot. How does it actually trap light?
Okay, so it turns out a magnetic dislocation is actually a combination of two things.
Two things, okay.
Yeah, so there's a topological defect and a magnetic domain wall.
Okay, those sound kind of intimidating.
They do. All right, well, let's break it down. So think of a topological defect like a whirlpool in a river.
Okay.
It's that point where the flow of water gets disrupted and it spins around.
I got you.
And that's kind of what's happening with the magnetic field lines around this dislocation point. They're just swirling around.
So a magnetic whirlpool, that makes sense.
Yeah.
What about this magnetic domain wall?
Okay, well, imagine you have a fence separating two properties.
Right.
And on one side, the grass is green. On the other side, it's brown.
Okay.
That fence, that's like the domain wall. It marks the boundary between two areas with different properties. In this case, it's the magnetic orientation that's different on either side of the wall.
Okay, so we got this magnetic whirlpool, and then there's like a fence running right through it.
Exactly.
How does that trap light?
It's the combination.
Right.
Right. The whirlpool, or the topological defect, acts as a focal point. It concentrates the light. And then that domain wall, that acts like a guide. So the light is confined along a specific path.
So the light gets sucked into the whirlpool, and then it's forced to follow the fence line.
Exactly.
That is super cool. So the light can be trapped in different ways too, right?
Yes, that's right. The researchers found that light can be trapped in two main ways: point localization and line localization.
So like a tiny concentrated point of light versus light spread out along a line.
Precisely. And to measure how tightly trapped the light is, they use something called the inverse participation ratio.
Okay.
Think of it like a light trap score. The higher the score, the more tightly the light is held.
A light trap score.
Yeah.
Gotcha. Okay, so we can trap light, but can we do anything else with it once it's trapped?
Oh, we can do a lot. So remember those different ways light can be trapped. Well, by adjusting the strength of the magnetic dislocation, we can actually change the color of the light that gets trapped.
Whoa, really?
It's like creating a rainbow of trapped light, each color at its own specific point.
That's incredible. It's not just trapping the light, it's like we're controlling it too. But this all sounds very theoretical. Did they actually prove any of this works?
That's where the simulations come in. They basically built a virtual model, like a computer game, for light, to see how it would behave around these magnetic dislocations.
Oh, cool. So what did they find?
Well, they actually saw both types of light trapping, point and line, exactly as predicted, but they found something even more important, too.
What's that?
Even if there are imperfections in the system, the light stays trapped. It's like the magnetic whirlpool doesn't fall apart even if you toss a few pebbles into it.
Oh, wow. So it's pretty robust.
Very robust. And that's really important for making this work in real life because nothing's ever perfect, right?
Right.
So, yeah, this means this technology could actually work.
So what's next? I mean, are we going to see magnetic dislocations in our smartphones anytime soon?
That's the big question, isn't it? I mean, the simulations are really promising, but there's still a gap between that virtual world and a physical device. So the next challenge is figuring out how to actually build these magnetic dislocations using real materials.
Right, like going from a computer model to something you can hold in your hand.
Exactly. So they've suggested a few potential platforms, like using something called synthetic frequency lattices, or maybe curved waveguide arrays.
Uh, okay, those sound a little complicated.
They do. All right. Well, imagine instead of physically twisting a magnetic field, you create a virtual lattice out of different frequencies of light.
Okay.
So that's essentially what a synthetic frequency lattice is. Instead of bending a physical material, they're bending light itself.
Whoa. Okay, I think I'm following. What about those waveguide arrays?
All right, think of a waveguide like a fiber optic cable that guides light along a path. So by carefully designing the shape of these waveguides, you can essentially create magnetic fields for light.
So they're building these tiny racetracks for photons,
Hmm.
and the track itself creates the magnetic twist.
Yeah, exactly.
That is so clever.
It is. And these are just two examples. There are probably many other ways to build these magnetic dislocations, and I know researchers are exploring all sorts of possibilities.
It sounds like we're about to enter a whole new era of manipulating light.
I think it's safe to say that we are witnessing something truly revolutionary here.
Wow. Okay, let's maybe take a step back for a second and talk about what we could actually do with this. I mean, what kind of real-world problems could magnetic dislocations actually solve?
Well, the possibilities are pretty vast, but one area that really stands out is optical computing.
Optical computing.
Yeah, imagine using light instead of electricity to perform calculations.
That would be way faster.
Lightning fast.
Yeah.
And magnetic dislocations could be the key to building these next generation optical circuits.
So instead of electrons zipping around circuits, we'd have photons racing through these magnetic dislocations.
Exactly.
That is wild. What about communication? Could these dislocations change the way we send data?
Absolutely. Imagine sending data encoded in light beams, trapped and guided by magnetic fields.
So instead of radio waves, we'd use light waves.
It would be incredibly fast and basically unhackable.
Sounds like sci-fi.
Right. And then there's energy harvesting. Imagine super efficient solar panels that capture and concentrate sunlight using magnetic dislocation.
So we'd have these magnetic light traps converting sunlight into energy instead of traditional solar panels.
Exactly.
This is all incredibly exciting. But are there any downsides or challenges we need to be aware of?
Of course. No technology is perfect, right? One of the biggest challenges is figuring out how to build these things on a larger scale. Right now, we're talking about manipulating light at the nanoscale. So to make practical devices, we need to figure out how to scale that up, and that's a huge challenge.
So it's like going from building a model airplane to constructing a real jet.
Exactly. And then another challenge is just understanding this whole dance between light and matter in these magnetically distorted environments. I mean, there's still so much we just don't know about how light behaves under these conditions.
Right.
So yeah, there's a lot more research to be done.
Well, that's the beauty of science, right?
It is. It's a journey. And with every discovery, there are a million more questions.
Speaking of questions, this research paper focuses on trapping light. But could this concept be applied to other types of waves, like sound waves?
That's a great question, and it's one that researchers are already looking into. I mean, it's totally possible that we could apply these principles to a whole range of waves, not just light.
So we could see things like magnetic sound barriers or even magnetically controlled acoustic devices.
Exactly. Imagine being able to shape and control sound with the same precision that we're starting to have with light.
This whole concept of magnetic dislocations is just mind-blowing. It's like science fiction is becoming reality right before our eyes.
I know. It really is. It's amazing what can happen when human curiosity and ingenuity come together, right?
It is. All right, well, before we get too carried away thinking about all the possibilities, let's get back to the research. I want to hear more about those applications we touched on earlier.
Oh, yeah, those applications are definitely worth exploring in more detail. They really show how much control we could have over light. Yeah, those applications are really cool. But before we get to those, let's talk a little bit more about those simulations.
Okay, yeah, good idea.
They're kind of the backbone of this whole paper, right? They're giving us proof that these magnetic dislocations are more than just an idea. Like we could actually create these things.
Yeah, that makes sense.
Okay.
Okay, so walk me through this. How do you even simulate something like twisting a magnetic field?
Well, you start by building a virtual model of that 2D lattice we were talking about. Remember those hopping
Oh,
phases?
yeah, those were pretty wild.
Yeah, they basically tell the light how to move through the lattice, right?
Exactly.
So in the simulation, those hopping phases become like instructions for the light. They're coded into the model.
So the researchers are basically setting the rules of the game for the light waves.
Yeah, and then to actually create the magnetic dislocation, they tweak those hopping phases in a specific way. Like they're creating a little magnetic vortex in this virtual world. Oh, wow. Okay. So they've built their little magnetic playground. How do they get the light in there?
Well, they simulate a light source, like a little pulse of light, and they fire it into the lattice. And then they just watch what happens.
So it's like they're running experiments on light, but it's all in a virtual reality lab.
Exactly.
Yeah.
And that's one of the great things about simulations. You can test all these different scenarios, tweak parameters, and really get a deep understanding of how these dislocations work.
It's like having a light laboratory at your fingertips.
It is. So what they found was really amazing. Remember how we were talking about the light being trapped in different ways, like at a point or along a line?
Yeah.
Well, the simulations actually showed both of those things happening, just like they predicted.
Wow.
But there's more. They also discovered that even if the system isn't perfectly uniform, like in the real world,
Right.
even then the light stays trapped.
That's huge. For real world applications, I mean, nothing's ever going to be perfectly symmetrical. Exactly. So that robustness is really important. It basically means that this technology has a chance. Like it could actually move beyond just theory.
Okay, so these simulations are really promising, but what's the next step?
Well, that's a good question. I mean, the simulations are great, but there's still a gap between that virtual world and actually building a device that works.
Right.
So the next challenge is figuring out how to build these magnetic dislocations in real materials.
Okay, so going from the computer model to something you can hold in your hand.
Yeah, exactly. They've suggested a few potential platforms, like using something called synthetic frequency lattices, or maybe curved waveguide arrays.
Those sound complicated.
A little bit, but let me try to explain. So imagine instead of physically twisting a magnetic field, you create a virtual lattice out of different frequencies of light.
Okay.
That's basically what a synthetic frequency lattice is.
So instead of bending a physical material, they're bending the light itself.
Exactly. It's like using the different colors of the rainbow to build a structure that can trap light.
Well, okay, I think I'm following. What about those waveguide arrays?
Okay, so think of a waveguide like a fiber optic cable that guides light along a specific path.
Okay.
So by carefully designing the shape of these waveguides, you can basically create magnetic fields for light.
So they're building like these tiny racetracks for photons, and the track itself creates the magnetic twist.
Exactly.
That's incredible.
It is pretty cool. And these are just two examples. I'm sure there are other ways to build these magnetic dislocations. And I know researchers are working on it.
Wow. It sounds like we're really on the verge of something big here, like a whole new way of manipulating light.
I think we are. I think it's safe to say we're seeing something truly revolutionary here.
Okay, so before we get ahead of ourselves, let's bring it back down to earth for a minute. What could we actually do with this? What real-world problems could this solve?
Well, the possibilities are huge. But one thing that jumps out is optical computing.
Optical computing.
Yeah. Imagine using light instead of electricity to do calculations.
And that would be way faster.
Right. So much faster. Magnetic dislocations could be the key to building those next-generation computers.
So instead of electrons going through circuits, we'd have photons racing through these magnetic dislocations.
Exactly.
Wow. What about communication? Could these dislocations change how we send data?
Absolutely. Imagine sending data encoded in light beams, trapped and guided by magnetic fields.
So like instead of radio waves, it's light waves.
Yeah. It'd be unbelievably fast and basically impossible to hack.
That sounds straight out of a sci-fi movie.
I know, right? And then there's energy harvesting. What about super efficient solar panels that use magnetic dislocations to capture sunlight?
So instead of traditional solar panels, we'd have these magnetic light traps converting sunlight into energy.
Precisely.
This is all so exciting. But I have to ask, are there any downsides or challenges that we should be thinking about?
Yeah, of course. Nothing's perfect, right? One of the biggest challenges is figuring out how to build these things on a larger scale. You see, right now we're talking about manipulating light at the nanoscale.
Right.
But to make devices that we can actually use, we got to figure out how to scale that up. And that's not easy.
So like going from a model airplane to building a real jet.
Exactly. And then there's the whole issue of really understanding how light and matter interact in these magnetically distorted environments. There's still so much we just don't know about how light behaves under these conditions.
So there's still a lot of research to do.
Oh, yeah, tons. But that's the fun part, isn't it?
It is. That's what science is all about. Always more to discover.
Exactly.
Speaking of discovering new things, this research is all about trapping light. But could we use this concept for other types of waves? Like what about sound waves?
That's a great question. And actually, some researchers are already looking into that. I mean, it's totally possible that we could apply these principles to other kinds of waves, not just light.
So things like magnetic sound barriers,
Right.
or even magnetically controlled acoustic devices.
Exactly. Just imagine being able to shape and control sound as easily as we're starting to do with light.
This whole concept is just mind-blowing. It's like we're watching science fiction become reality.
I know, it's amazing, right? It just goes to show you what happens when you combine human curiosity with a bit of ingenuity.
I agree. All right, well, before we get too lost in all the what-ifs, let's get back to the research. We talked about some potential applications earlier. I want to hear more about those.
Oh, yeah, those applications are definitely worth digging into. They really show just how much control we could have over light with this technology.
Okay, so let's talk about those applications. There were two that really caught my attention.
Mm.
Selective excitation and adiabatic pumping.
Yeah, those are definitely some of the coolest parts of this whole paper. They really highlight just how much control we could have over light with this technology.
Let's start with selective excitation.
Yeah.
So it's kind of like having this magnetic dial that lets us tune into different frequencies of light, right?
Yeah. Exactly. It all comes back to that rainbow effect we talked about. Remember how different frequencies, different colors of light get trapped at different points depending on how strong the magnetic dislocation is?
Yeah, like each color has its own sweet spot in the magnetic field.
Exactly. So selective excitation uses that principle. Imagine you've got a beam of light with a whole spectrum of colors, like a rainbow, all mixed together. Well, by adjusting the strength of the magnetic dislocation, we can essentially create a trap that only captures a very specific color.
So it's like setting a magnetic snare for one specific color of light and letting all the others just pass through.
That's a great way to put it, like plucking a single note out of a complex chord.
Wow. And how precise can they get with this? Could they isolate a single shade of red, for example?
Well, in the simulations, they were able to target individual frequency components within a broad spectrum of light.
So yeah, they could probably isolate a single shade of red. That's amazing. I can see how this could be huge for things like optical communications.
Oh, absolutely. Imagine sending data encoded on different colors of light, and they're all traveling down the same fiber optic cable. Each color would carry a different stream of information.
It's like having multiple lanes on a highway, but for light instead of cars.
Exactly. And because each channel is encoded on a specific color, it would be incredibly secure. You'd need to know exactly how to tune the magnetic field to unlock each channel.
So it's like a combination lock, but for light signals.
Exactly. Selective excitation really opens up a whole new world for how we can send and process information using light.
Okay, so we can trap specific colors of light.
Yeah.
But what about moving that trapped light around? That's where adiabatic pumping comes in, right?
That's right. So remember how we were talking about those two different ways light can be trapped at a single point or along a line?
Yeah, the point and line localization.
Right. Well, adiabatic pumping is all about smoothly shifting the trapped light between those two states. So by gradually changing the strength of the magnetic dislocation, we can move the light from a point to a line or back again.
So we can basically make the trapped light expand and contract, like a magnetic accordion.
Huh. I like that. And we can even release the light completely by slowly weakening the magnetic dislocation until it disappears.
Wow. It's like having a light switch that not only turns the light on and off, but can also guide it and reshape it.
That's a great way to put it. It gives us incredible control over the movement and manipulation of light, all using magnetic fields.
And what kind of applications could this lead to?
Well, one really exciting possibility is using it to create optical circuits. Imagine building transistors and switches and logic gates, all based on guiding light with magnetic fields.
So instead of having electrical circuits etched onto silicon chips, we'd have optical circuits controlled by magnetic dislocations. It's like building a computer out of light.
That's the idea. It could revolutionize the way computers work, making them faster, more efficient, and maybe even more powerful.
This has been an incredible deep dive. We've gone from twisting magnetic fields to trap light, all the way to imagining computers that run on light beams. It's amazing to think about what other incredible applications are out there waiting to be discovered.
I know, it really is. And it's a testament to the incredible work of these researchers.
Absolutely. We've learned about this new way to manipulate light, explored the simulations that show us it's possible, and even caught a glimpse of some potential applications that could change everything from the way we compute to the way we generate energy.
It's a remarkable discovery with huge implications for the future.
And as with any big scientific breakthrough, this is really just the beginning.
There's still so much we don't know about magnetic dislocations, and I'm sure scientists will be busy exploring their full potential for years to come.
Absolutely. So as we wrap up this deep dive, we'll leave you with one final thought to ponder. If we can twist magnetic fields to trap and manipulate light, could we do the same with other forms of energy? What about sound waves? Or even something even more exotic?
That's a fascinating question. The possibilities are endless, and who knows what incredible discoveries are waiting for us just around the corner.
That's it for this episode. We hope you've enjoyed this journey into the mind-blowing world of magnetic dislocations. Until next time, keep exploring, keep questioning, and keep diving deep into the wonders of science.